Hi students, in this session I am going to explain catalyst control asymmetric synthesis. Okay, what is the definition of catalyst control asymmetric synthesis? In this method, a chiral catalyst is responsible for formation of unequal amounts of enantiomers or diastereomers as products. This is also known as chiral catalyst control asymmetric synthesis or fourth generation asymmetric synthesis. I repeat once again. In this method, chiral catalyst is only responsible for formation of unequal amounts of enantiomers or diastereomers as products. Okay, in this reaction, write down the generalized or common reaction. Okay, a chiral substrate molecule on treated with a chiral substrate molecule on treated with a chiral reagent by using a chiral catalyst. Okay, in asymmetric synthesis, one of the component, either is a substrate, a reagent or catalyst, must be a chiral. Okay, in fourth generation asymmetric synthesis or catalyst control asymmetric synthesis, catalyst is chiral. Okay, then it produces unequal amounts of enantiomers or diastereomers. Okay, D1 diastereomer 95%, D2 diastereomer 5%, or unequal amounts of enantiomers E1 95%, E2 5%. Okay, let us consider an example. Epoxidation of alkenes by a chiral reagent to produce equal amounts of enantiomers. Okay, alkenes on treated with a chiral oxidizing agents, epoxidation reagents are like metachloroparabenzaic acids. Metachloroparabenzaic acid. Okay, alkene on treated with metachloroparabenzaic acids to gives 50% of beta epoxide and 50% of alpha epoxide. It is alpha epoxide, it is beta epoxides. Okay, in the above reaction, all the molecules, substrate, reagent, solvent are achiral. It is not a asymmetric synthesis. Okay, epoxidation is syn addition, as anti-epoxidation not possible. In the above reaction, addition of oxygen atom to olefin both re and psi phases to produce a equal amounts of enantiomers. In the above reactions, you are using the achiral reagent. Okay, achiral reagent undergoes oxidation reaction to gives equal amounts of enantiomers as products. In this reaction, metachloroparabenzaic acid is also a chiral reagent. It doesn't differentiate posterior center. Okay, in this reaction you are using to achiral solvents dichloromethane. Okay, dichloromethane doesn't differentiate posterior center. Substrate molecule also be achiral. Okay, then in these reactions we get a 50% of one isomer, another 50% of another isomer. Okay, 50% of beta epoxide and 50% of alpha epoxides. Okay, it is not a asymmetric synthesis. Okay, on that conditions, some olefin systems undergoes oxidation reaction with some other oxidizing agents to gives a selective epoxides. Either the reaction it gives 90% of alpha epoxides and 90% of beta epoxides. On that conditions, you are using to a chiral catalyst. Okay, Sharpless epoxidations is a well-known epoxidation reactions to produce unequal amounts of alpha epoxides or beta epoxides. Okay, first, what is Sharpless epoxidation? The enantioselective epoxidation of primary allylic alcohols by using titanium tetraisopropoxides, tertiary butyl hydrogen peroxide, and a chiral catalyst diethyl tartrate is called as Sharpless epoxidation. I repeat once again. The enantioselective epoxidation of primary allylic alcohols by using titanium tetraisopropoxides, tertiary butyl hydrogen peroxide, chiral diethyl tartrate is called as Sharpless epoxidation. Okay, in this reaction, titanium isopropoxides is a acyl reagent. Tertiary butyl hydrogen peroxide is also oxidizing agent. It is a acyl reagent. A chiral catalyst, diethyl tartrate. Okay, diethyl tartrate is a chiral molecule, undergoes oxidation reactions to gives 95% of alpha epoxides and 5% of beta epoxides. Okay, in this reaction we observe that first thing, allylic alcohols, okay, primary allylic alcohols and reacts with titanium isopropoxides, tertiary butyl hydrogen peroxides plus that, okay, plus diethyl tartrate, okay, plus form of diethyl tartrates. Okay, it gives 90% of 95% of alpha epoxides. Okay, again same primary alcohols on treated with titanium isopropoxide, tertiary butyl hydrogen peroxides, minus that it gives 95% of beta epoxides and 10% of 5% of alpha epoxides. Okay, in sharpless epoxidation, primary allylic alcohols, tertiary butyl hydrogen peroxides and titanium isopropoxide are acyral. But that diethyl tartrate is a chiral catalyst. It produces the unequal amounts of enantiomers. In sharpless epoxidation, generally used primary allylic alcohols. These are the some of the examples in sharpless epoxidation reactions. Okay, in sharpless epoxidations, most probably it takes a primary allylic alcohols. In most of the cases, it takes primary allylic alcohols. Generally used primary allylic alcohols are these are the some of the primary allylic alcohols. Okay, the double-bond system having some monoalkyl substituents, dialkyl substituents. Okay, dialkyl substituents in different carbon atoms, trialkyl substituents. Okay, in sharpless epoxidation, generally used hydrogen peroxides. Okay, generally used hydrogen peroxides are trimethyl or tertiary butyl hydrogen peroxides. Okay, tertiary butyl hydrogen peroxides are some of the phenyl derivative of hydrogen peroxide, phenyl derivative of hydrogen peroxides. Okay, in sharpless epoxidation, generally used chiral catalyst. Okay, in this reactions, the chiral catalyst is diethyl tartrate. Diethyl tartrate. Okay, tartrate is a diethyl tartrate is a ester of tartaric acids. Ester of tartaric acids. Okay, these are the two forms of plus det and minus det. This is plus det, RR form of diethyl tartrate and SS form of diethyl tartrates. Okay, what is the relation between plus and minus forms? Enantiomeric relations. Okay, plus det and minus det. Okay, both are chiral molecules. It acts as a chiral catalyst. Okay, another important reagent is titanium tetraisopropoxide. Titanium tetraisopropoxides. It is also a chiral reagents. Okay, let us consider reaction. Primary allylic alcohols on treated with titanium isopropoxides and tertiary butyl hydrogen peroxides plus det. Okay, plus det. Okay, plus det, it gives 95% of alpha epoxides and 5% of beta epoxides. Okay, this is plus det form. Okay, in this reaction, okay, we observe the mechanism. Okay, first thing, titanium tetraisopropoxides are coordinated with plus det by loss of 2 moles of 2 moles of isopropanol. It gives corresponding ethers. Okay, it gives corresponding ethers. Okay, the formed ethers again ion reacts with allylic alcohols and tertiary butyl hydrogen peroxides. Okay, displacement of another 2 isopropoxy groups with allylic alcohol and tertiary butyl oxide induce corresponding tetracoordinate complex. Okay, first thing, tetracoordinate titanium complex on reacts with plus that or minus that, it gives corresponding tetracoordinate complex. Again, this tetracoordinate complex are treated with hydrogen peroxide, tertiary butyl hydrogen peroxide and allylic alcohol to gives again tetracoordinate complex. Okay, this tetracoordinate complex undergoes oxidation reactions. Finally, it gives 95% of alpha epoxides and 5% of beta epoxides. Okay, it is 95%, it is 10%, 5%, sorry, 5%. Okay, the detailed mechanism of sharpless epoxidations. Okay, the detailed mechanism of sharpless epoxidation. First thing, in sharpless epoxidation, titanium tetrapropoxides, tetraisopropoxides, and coordinate with that, it gives tetracoordinate complexes. Okay, the tetracoordinate complex exists into dimer. Okay, it is a dimer. We observe that titanium in hexacoordination. Okay, the dimer form of titanium isopropoxide tetra coordinate derivative in dimer form. Okay, in dimer form we observe that titanium in hexacoordinate form. Okay, hexacoordinated form. Okay, two titanium tetra isopropoxides to combine to forms a dimer and to forms a dimer with hexacoordinated. Okay, again these compounds are treated with allylic alcohols and tertiary butyl hydrogen peroxides by exchanging of two oxygen atoms or exchanging of coordination number with allylic alcohols and tertiary butyl hydrogen peroxides. It gives again dimer form of hexacoordinated titanium complex, hexacoordinate titanium complex. Okay, in this hexacoordinate complex, we observe that two things. One is distal oxygen, proximal oxygen. Distal means some nearer to posterior center. Okay, distal oxygen means nearer oxygen. Okay, nearer oxygen. It is nearer to posterior center. Okay. In this Shimpora complex, okay, this is posterior center, it is nearer to distal oxygen. Okay, posterior center present at above the plane. Okay, there is any specifications, plane representations, dark wedge or broken wedge. Okay, this allylic posterior center present at top face and distal oxygen present at bottom face. Okay, I read again. Okay, this posterior center in top face, the distal oxygen in bottom face undergoes oxidation reactions to gives corresponding alpha epoxides. Okay, in this mechanism, we observe only two things. The distal oxygen is nearer to posterior center. Okay, then it undergoes oxidation reactions. Then it gives corresponding alpha epoxides. Okay, we observe the above mechanism. The Shimpora complex, allylic alcohol is sterically free from the bottom for the bottom face of and distal oxygen addition to below the plane to produce alpha epoxides. Okay, I repeat it once again. In the above mechanism, the Shimpora complex observed that the allylic alcohol is sterically free. The distal oxygen is nearer to the distal oxygen present below the plane. It is nearer to posterior center. Undergoes oxidation reactions to forms alpha epoxides. Okay. Again, similarly, primary allylic alcohols are treated with minus that. Okay, minus that first to titanium to forms a hexacoordinated dimer complex. Okay, this dimer complex again on exchanging of ligands like allylic alcohols, tertiary butyl hydrogen peroxides to gives again Shimpora complex. Okay, Shimpora complex. Okay, this Shimpora complex we observe that the primary allylic alcohol and distal oxygen. Okay, this is distal oxygen. This is proximal oxygen. Okay, distal oxygen presented above the plane. The posterior center presented below the plane. Okay, then it undergoes oxidation reactions then it gives 95% of beta epoxides and 5% of alpha epoxides. Okay, in this reaction we observe that epoxidation takes place in above the plane. In the above mechanical Shimpori complex, the allylic alcohol sterically free for the top phase and distal oxygen addition to above the plane to produce beta epoxides. Okay, first thing, titanium tetraisopropoxide and coordinated with plus and minus catalyst, it produce corresponding tetracoordinate complexes. Again, tetracoordinate complex exists into dimer. Okay, under conditions we observe that hexacoordinate complex of titanium. Okay, hexacoordinate complex by exchanging of ligands, allylic alcohols and tertiary butyl hydrogen peroxide, it gives corresponding Symporia complex. Okay, we observe Symporia complexes, the allylic carbons, the allylic group and distal oxygen. Okay, distal oxygen, in case the distal oxygen present in below the plane, okay, it undergoes oxidation reactions below the plane, it gives alpha epoxides. The distal oxygen present in above the plane, it undergoes oxidation reactions to gives beta epoxides. Okay, in the second reactions, the primary allylic alcohols are treated with minus dead titanium isopropoxides, tetraisopropoxides and tertiary butyl hydrogen peroxide to gives 95% of beta epoxides and 5% of alpha epoxides. Okay, the catalyst titanium tetraisopropoxides and plus dead combine to forms to rapid exchange of two alkyl ligands to gives tetracoordinated bidentate titanium complex. Okay, this complex reacts with primary allylic alcohols and tertiary butyl hydrogen peroxide, exchanging of other two alkoxyl ligands to gives a Shimporia complex. Okay, in this complex, proximal peroxygen coordinated with titanium bifacilitates releasing of distal peroxygen to double bond and allylic, the double bond of allylic alcohols acting as a nucleophile and distal peroxygen acts as a electrophile. Okay, distal oxygen acts as electrophile. It undergoes oxidation reactions to gives corresponding alpha epoxide and beta epoxides. Okay, plus that has ability to recognize rephase of the compound and the produce major alpha epoxides. In the case of minus that has ability to recognize psi phase of compound to produce a major beta epoxides. I repeat once again. In plus that has ability to recognize rephase of the compound and produce a major alpha epoxides, and minus that has ability to recognize psi phase of the compound to produce a major beta epoxides. In sharpest epoxidation, electron withdrawing group decrease the rate of the reactions, electron releasing groups increase the rate of reaction, but the groups does not enhance the stereochemistry of epoxidation. Okay, I repeat once again. In sharpest epoxidations, the reacted molecule and the substrate molecule having electron withdrawing groups decrease the rate of reactions. Electron releasing groups increase the rate of reactions, but the groups doesn't enhance the stereochemistry of epoxidation reactions. Okay, this is sharpless epoxidations. Okay, I repeat once again. Okay, in sharpest epoxidation reactions, okay, first thing, substrate molecule are treated with titanium tetraisopropoxides, tertiary butyl hydrogen peroxide and plus that, it gives 95% of alpha epoxides and 5% of beta epoxide. First molecule, titanium tetraisopropoxide and reacts with plus that, it gives tetracoordinate complex. Again, this tetracoordinate complex by exchanging of ligands to gives corresponding tetracoordinate complexes. This tetracoordinate complex finally undergoes oxidation reaction to gives alpha epoxides and beta epoxides. Okay, in these reactions we observed okay, tetracoordinate titanium complexes. In Shimporia complex view, it is hexacoordinate. It is not a hexacoordinate complex. Most probably, in titanium complex, we observe that the coordination number is 4. Okay, these are the partial bonds. Okay, by exchanging of ligands, finally it gives corresponding a Shimporia complex, distal oxygen and proximal oxygen. Okay, the distal oxygen below the plane, then it gives alpha epoxide. The distal oxygen present in above the plane, then it gives beta epoxides. Okay, this is sharpless epoxidation. Okay, again we read some of the applications. Okay, first thing, reactant molecule. Okay, it is a secondary allylic alcohols are treated with titanium isopropoxide in the presence of tetrahydrobutyl plus that. Plus that gives alpha epoxides. Okay, it is a specific diastereomer because okay, it is a chiral center. It is also chiral center. Okay, two chiral center. It is a diastereomers because it is chiral allylic alcohol. Okay, in case in sharpless epoxidation we take a chiral alcohols, it gives corresponding diastereomer. Okay, again second example. Okay, it is a allylic alcohols and react with titanium isopropoxide and tetrahydrobutyl. It gives beta epoxide. It takes minus that. Okay, in this reaction, it is a allylic alcohol, secondary allylic alcohols, and treated with minus that. Again, it gives alpha epoxides. Okay, in sharpless epoxidation reactions, alcohols are arranged into different positions. That means, okay, in sharpless epoxidations plus that, distal oxygen always gives alpha epoxides. In sharpless epoxidation minus that, it gives beta epoxides. Okay, in sharpless epoxidation plus dates easily distinguish rephase or easily recognize rephase. Okay, use minus that, it easily recognize psi phase, then it gives corresponding beta epoxides. In case the distal oxygen recognize to rephase, then it gives alpha epoxides. Okay, this is short level epoxidations, reaction mechanism, and finally some of the applications. Okay, the next topic is Jacobson catalyst. This reaction is mainly used for the epoxidations of unfunctionalized olefin systems. Unfunctionalized olefin systems can be oxidation by using Jacobson catalyst. Okay, sharpless epoxidation is not used for the epoxidation of simple olefins. It is not in that conditions we are using to Jacobson catalyst. Okay, I repeat once again. Sharpless epoxidations not useful for epoxidation of simple olefin systems. In that conditions you are using to Jacobson catalyst. Okay, Jacobson's observe that transition elements ferrous, manganese, ruthenium and chromium having able to take up an oxygen by changing the valency. Okay, preparations. Okay, Jacobson catalyst derived from 1,2 diamino cyclohexane and 2,4 di-tetrahydrobutyl tetrahydrobutyl silaldehyde. Tetrahydrobutyl silaldehyde. Okay, 2,4 di-tetrahydrobutyl silaldehydes. Okay, silaldehydes in the presence of manganese metal to gives corresponding beta epoxides. Okay, sodium bleach acts as oxidizing agent. Okay, bleach is NaOCl. Okay, sodium oxychloride acts as a oxidizing agents. Okay, in these reactions, first diamino cyclohexane untreated with 2,4 di-tetrahydrobutyl silaldehydes in the presence of manganese metal and bleach sodium hypochlorite, it gives corresponding Jacobson catalyst. Okay, in this reaction, it is a Jacobson catalyst. Okay, Jacobson catalyst selectively used for oxidation of non-functionalized alkene systems. It is a highly anisotrophic reagent for preparation of beta epoxides from unfunctionalized olefin systems. Unfunctionalized olefin systems. It is highly selective epoxidations of E and Z alkenes to give corresponding beta epoxides. Okay, what is the specialty of Jacobson catalyst? It is selectively oxidation with unfunctionalized olefin systems to give corresponding beta epoxides. It is a highly selective reagent. Okay, write the reactions. Okay, Z alkenes on reacts with Jacobson catalyst, it undergoes oxidation reaction to give beta epoxides. Okay, Jacobson catalyst is selective reagent for epoxidations to get selectively beta epoxides. Either Z alkenes or E alkenes, it must give beta epoxides. Okay, mechanism of the reaction. Okay, observe that. Okay, in Jacobson catalyst, the oxygen. Okay, view of the molecule, the oxygen present in above the plane. Okay, then it undergoes oxidation reactions, we get beta epoxides. Okay, the catalyst always presented above the plane, then it gives beta epoxides. Okay, by formation of a transition state. Okay, epoxidation always takes place in beta plane. Okay, applications, some of the applications of Jacobson catalyst. Okay, in Jacobson catalyst, asymmetric epoxidation reactions, either you take E alkenes or Z alkenes, it gives beta epoxides. Any olefin system, unfunctionalized olefin system, any unfunctionalized olefin systems are treated with Jacobson catalyst, it gives corresponding epoxide. It is also beta epoxide, it is also beta epoxides. Okay, any alkene systems, okay, it must gives some of the beta epoxides. Either it is E alkenes or Z alkenes, it must gives beta epoxides. Okay, I repeat once again, Jacobson catalyst. Okay, it is a selective useful reagent for unfunctionalized olefin systems. Okay, Sharpless epoxidation is only useful for epoxidation of simple olefin systems. Okay, it is used to unfunctionalized olefin system, either E alkenes or Z alkenes, and reacts with Jacobson catalyst. It gives beta epoxides. Okay, Jacobson catalyst prepared from diaminocyclohexane and 2,4 ditetrachlbutyl silaldehydes in the presence of manganese metal and sodium hypochlorite bleach. It gives corresponding Jacobson catalyst. Okay, this is Jacobson catalyst and reacts with alkene system to gives corresponding beta epoxides. Okay, in the next session I am going to explain asymmetric Wilkinson catalyst and Nauri catalyst. Thank you to all.